Let's start with a repetition of the last lecture. In the last lecture, we spoke about lossy source coding or the rate distortion theorem. So first I want to explain how quantization is related to rate distortion. So in digital communication, relies on converting source signal into bits. And if you convert a source signal, then the waveform is digitalized. That means it's sampled in time and quantized in value. Because of the sampling theorem, that guarantees that you can quantize without losing information. But however, practically, you lose information by quantizing analog sampled values to bits. And somehow the rate distortion theorem or the theory in general characterize the limits of this quantization. So the quantization is a process of representing signals by a finite number of bits. So from this perspective, quantization is the same as lossy source coding or lossy compression. And remarkable rate reduction is achieved by coding over long sequences of bits. But let's look at the definition more formally. So we assume that we have a discrete memberless source with alphabet X, which emits a sequence xn that is passed to the source encoder. And the encoder quantized X into 2 to the nr sequences, X hat n of W, and sends the index to the decoder. Perhaps we can quantize it into bits. Then we have exactly log 2 to the nr sequences or log nr sequences. The decoder puts out the reconstruction x hat of n of xn. And the letter x hat I take on values in the alphabet X. Normally we assume that x hat is the same as X. And the goal is now we want to ensure that a non-negative real-valued distortion between xn and x hat of n is within some specific value d. So we want to have that this value here is less or equal the distortion d, big D. So what we want to have, we want to encode xn in such a way that the decoded x hat n, or the expected value of this distortion, is smaller or equal d. So we want to have that the distortion between these two sequences is small. We can choose here any measure. So some examples for measures. Typical measures are, for example, the Hamming distance. It's well known. And we take the average Hamming distance between the sequences. So the distortion, the Hamming distortion between xn and x hat n is the average over the distance, the Hamming distance between these two sequences. So xi is not equal x hat I, then this is 1. And if it's equal, then it's 0. Just count the average number of positions where the sequences are different. Another possible distortion measure is the Euclidean distance, or the squared error distortion. In this case, the distortion between xn and x hat n is defined as the average Euclidean distance here. As in the example, we always will consider the distortion function in this form that we look at the average of the distance of the letter-wise distortion. Now we can formulate the rate distortion problem. So first I want to remember that we can consider now two different problems. So we can look at the smallest rate r as a function of the distortion. This is called the rate distortion function, what we will do. But of course we can also look for the smallest d as a function of r. This would be called the distortion rate function. So instead of fixing d, we can fix r and search for the smallest d. But we will fix d and search for the smallest r. So how we can get this? So we construct a random code book. As for the channel coding theorem, we begin by choosing a channel. That's now very special. We choose a channel px hat x, so a channel from x to x hat, like you know it from channel coding, but we can choose any channel. And if we have chosen a channel and we get an output sequence output, then we can calculate it. So we can also calculate the margin if we know the distribution of the source and we have the channel, then of course we can calculate the margin distribution of the joint distribution x hat. And then we can use this margin distribution to create the code book randomly. So each letter we will create randomly, and then we give the code book to the encoder and to the decoder. So here again the code construction. We generate 2nr code words of length n by choosing each of the n times 2 to the nr symbols independent using the marginal distribution. Then we, furthermore, we need one sequence more. This is the default code word. You will see we need this, which is equal r, where which is equal a, where a is the letter such the expected value of the distortion is equal to d max. Of course, we have now one code word more, but if you look at the way 2nr over 2nr plus 1, this rapidly approaches 1 when n is very large. So it's okay to choose this extra code word here. So we look at the encoder. What is the encoder doing? So the source produced some output xn. He chooses now some w that minimize the distortion between xn, x hat, and w, and send w to the decoder. So we will see he chooses a typical. We have this is the most, this should be jointly typical that this is fulfilled. And then the decoder put out the reconstruction x hat of nw. So the idea is here, you see again here the code book. So each of this letter is random, is independent produced. And here you see the random coding experiment. So we have this letter xn, and because which was put out by the source, and because of our channel, we got this sequences here and sent this to the encoder. He sent then w to the decoder by looking here, and the decoder produced out x hat n of w. Yes. So and the the idea is that we always choose it in such a way that x hat n and xn are jointly typical. And now, what is an error event? So we consider the error event that x hat n of w is not jointly typical with xn. Then we can use the theorem of total expectation. So we consider the expectation of the rate distortion xn and x hat n. And then we have here the probability of the error event and the probability of the opposite of the e to the c, that's the complement of the error event. And here we have the expected value under the condition that the error event happened, and here times the expected value of the distortion under the condition that the error event not happened. This is the theorem for total expectation, because we have the probability of the event plus the probability of the complement is of course equal 1. So by using this error event, we analyzed this and we get the following result, that the rate distortion is equal to the minimum over all possible channels we can choose from x to x hat, such that the expected value of the distortion is smaller or equal d of the mutual information of x and x hat. That we got by analyzing this strategy. And we also show that this is best possible. You see we have here an equal. And this we could do just by using the fact that the function Rd or Rid, what I defined here, is convex. And we use some property of the E function that 1 minus x is a tangent to e to the minus x. And we start again with nr is equal to the logarithm of x hat and greater equal than x hat and so on. And we end it here somewhere. That was the idea of the rate distortion function.